All right. Okay. Well, I guess we'll begin. Happy Monday. It's another week. Now week 8, and things are clicking by. Another homework. Okay. Well, we'll see, and we'll go. Okay. So this week we are going to introduce unsupervised learning, and our first topic is clustering. So just to kind of contrast this with everything we've done so far has been supervised learning. So that's like, the neural networks, the KNN, your support vector machines. I don't know, what have we done? We've done some stuff, okay? They've all been supervised learning. In that, supervised learning means you've got input values, and then you do something with them and you get some kind of output thing, right? You have a classification or a value. And it's supervised because your training data has an answer and you're trying to match that answer. So with the neural network, you had an output and you're trying to match that, right? You had the iris species, and you want your inputs to come out so that it matches what that output is, okay? So that's supervised. You have a target value, and you have your prediction, and we're able to measure the difference between the target and the prediction, okay? And that was pretty much how everything was driven when we did supervised learning. We said, here's our target, here's our prediction, and we want these two things to be as close as possible, right? The difference between them we called the loss, and we wanted to shrink the loss as much as possible. And it was like the squared difference and things like that. And we use gradient descent to say, okay, this is how we shrink the difference between what we're predicting and what the actual thing is. That's supervised learning. Okay. Unsupervised learning, there's no target values. Okay, you just get data, right? You just have kind of the matrix of X variables. And we're supposed to look for structure, or we're looking for something, some kind of pattern in this data. So a common thing is clustering, okay? As far as unsupervised learning goes, we can try doing clustering, and then another thing is dimension reduction, okay? And so we'll look at clustering this week, and next week or something we'll do PCA, principal components analysis, which is dimension reduction. Okay, and so clustering is kind of all about grouping similar objects together. So the goal of clustering is to create some kind of group where the objects within the group are similar to each other, and objects in different groups are different from each other, right? And so this is kind of, based on someone's items that they purchased or something like that. Can you create clusters of products so that, when you go on Amazon, it says, hey, check out these other things that you might be interested in, right? And that's proven to be effective at generating sales and stuff. Things like, advertising, similar type of stuff, right? If you have visited these websites or something, are you more likely to click these other links or things like that? You can kind of, people try to cluster, when it comes to like elections and stuff, they try to cluster groups of people and figure out, which voting blocks they can find and things like that. So lots of ways to cluster things. And, we're mostly going to be looking at clustering based on a numeric variable, right? Because clustering based on categorical variables, it's possible, but it already kind of, like, they're already split in categories, right? So if you're going to look at, say, I don't know, some categorical trait, what kind of vehicle does somebody drive, okay? And you have like SUVs, sedans, and trucks and things like that. You can effectively just split them on some kind of clustering, right? And it might be like, do we put the SUVs with the trucks? Are those more similar to each other? Or the SUVs more similar to the cars or something? And it depends on what it is that you're looking at. But the categorical variables already kind of end up forming subgroups in of itself, okay? But anyway, when we do clustering, the key idea is, how do you measure this idea of similarity? Yeah, right? With clustering, we want objects or observations that are similar to each other to be clustered together. And so how do we measure similarity? Okay? And we'll start off with some basic ideas for measuring similarity, and then we can deviate from that in the future. Okay? All right, applications of clustering, we got that. Okay, so today we're going to take a look at kind of your most basic or your most straightforward clustering algorithm, and this is called K-means clustering. K-means clustering. It's a very simple clustering algorithm, and the way we measure differences or similarity is by using Euclidean distance, right? So it's very, in 2 dimensions, Euclidean distance you can just measure with a ruler, and then in higher dimensions, it's basically, you take each coordinate, you take the difference and you square it, you add them up, square root the whole thing, okay? Now, I have to warn you, you have K-means clustering, and then we also had K and N, right? K nearest neighbors. And I think just because these 2 things have a K in them, they often get confused or mixed up or things like that. They're completely different, okay? In that K-means is unsupervised, and it's a clustering method, okay? Whereas K nearest neighbors is a classification method, right? It's supervised and it's used for classification. Is K nearest neighbors iterative in any way? There's no iteration in K nearest neighbors, right? You just have all the training data, you have your test observation, you measure your distance from your test observation to everything else, and then you go from there. That's it. There's no iteration. Whereas when we do K-means clustering, it's going to be iterative. We update this, we update that, we update this, we update that, and we keep going until we reach some kind of convergence, okay? So with K-means clustering, we're going to have clusters. Our clusters are going to be defined by their centroid. The centroid is basically just the mean of the points assigned to the cluster. So basically you say, all right, these observations belong to this cluster. What is the mean of these observations? And in 2 dimensions, you're going to get the mean of x1 and the mean of x2, or something like that. As far as the formula goes, we say mu, the mean of cluster K, is going to be the sum of the x's multiplied by the z. Okay, z is a 0 or a 1. It's 0 if it's not in the cluster, and it's a 1 if it's in the cluster. So basically, you're going to get the sum of the x's that are in the cluster divided by the total number of points that are in the cluster. And that's what this is, the sum of the z times the x divided by the sum of the z's. Okay, z is being a 0 or 1. It's just what's the average of the points that are in the cluster. Okay, and this is the algorithm. This is how it's going to work. Okay, so step 0, we decide how many clusters, the number of clusters K that we're going to search for, and there's some thinking that maybe a little bit of trial and error for that. But first, you decide how many clusters you're going to search for. And then the first step is we just randomly assign points to each of the clusters. Okay, we're going to just randomly assign points to the clusters. Once all of the values have been assigned to a cluster, you are going to calculate the centroid of the values in each cluster. And once you do that, you reassign the values to the clusters by associating values in the data set to the nearest centroid using, and here we'll use Euclidean distance. And then we just iterate, repeat steps 2 and 3 until we reach convergence. And we'll say convergence occurs when no points get reassigned to a new cluster. All right. Okay, let me go ahead and give you your first view quiz answer for today, which is the letter C. C as in cat. C as in cat. Okay. So, all right, let's try this out. Okay, so I'm going to start off with this very simple toy data set, 8 points in 2 dimensions, and they are graphed right here. Okay, so I've got 8 points total. And then if I said, hey, make a cluster, make 2 clusters here, I think we would say, okay, these 4 go together and these 4 go together, right? It's very clear and very obvious how this should go. But let's go ahead and try this out using the K-means clustering algorithm and see if it results in something that makes sense. Okay. So our first step, well, we're going to say how many clusters are we going to look for? I guess that's step 0. I'm going to say we're going to look for 2 clusters. Okay. And then once you say we're going to look for 2 clusters, we just go through all 8 points and we randomly assign all of the 8 points to a cluster. Okay. So I'm going to just randomly assign them. And so all I do is I'm going to just sample 1 and 2, and then I'm going to set them as assignments. Okay. And we're going to say if assignment is 1, Z1 is going to be, as an integer, so 0s or 1s. So 1 if it's assigned to cluster 1, and 0 if it's not. And we got 1 if it's assigned to cluster 2, Z2, and 0 if it's not. Okay. Oh, can you guys see this? The red and the black colors? It's a little bit hard to see on the projector. Okay. Well, these 3 points are red, and so are these 2 points, okay? And then here I have this point, and this point in black. So I've got 3 points assigned to the black cluster, 5 points assigned to the red cluster. And yeah, when you do random assignment, you're not necessarily going to get a 50-50 split, or the things get evenly split out. So there is a very small but non-zero probability that when you randomly assign points to a cluster, that one of the clusters gets no points assigned to it. So that could happen, and then you might just have to start with a new random seed to kind of redo this thing, okay? Depending on how many clusters you're looking for. But, yeah, there's a few kind of edge cases where a couple things could break because of the random nature, but a fairly low probability and fairly simple solution of just trying a new random seed. Okay. All right. So anyway, we're going to take the 5 red points and we're going to say, what is the mean of these 5 red points? And we're going to take the 3 black points and we're going to say, what is the mean of these 3 black points? And that will be the centroid for the red cluster and the centroid for the black cluster. Okay, so the coordinates in x1 and x2, we have 0, 0, I got 0, 1, 1, 0, 1, 1, and then I've got, what is this, 3, 3, 3, 4, 4, 3, and 4, 4, right? So these are the coordinates here. And remember, the formula for finding the mean is we're going to take the x multiplied by its z, and then we're going to add them up. Now again, it's really just the mean of the points that belong to that particular cluster. But as far as these 3 black points go, I've got 0, 0, 1, 1, and 4, 4, and I'm going to ask what is the mean of those 3 points? 0, 0, 1, 1, and 4, 4, and so basically the x1 mean is going to be 0 plus 1 plus 4 divided by 3. I get 1.667. And then I do the same for x2. I get 0, 1, 4, 3. And just by kind of coincidence, I also get 1.667 here. And then we do it for the 5 points that belong to cluster 2. And it's these 5 points. So we're going to do 0, 1, 3, 3, and 4. Divided by 5, we get 2.2. And then we do the other points, 1, 0, 3, 4, 3. Divided by 5, we also get 2.2. Okay, so I'm going to take these two clusters and then plot them. Is that all right as far as finding the means of each cluster? Okay. I could have also just used dplyr, and I could say, hey, group by the assignments, and then give me the means of x1 and x2. I get the same results, 1.667, 2.2. Okay, so here's the mean, and I apologize for the difficulty here, but this one is the black centroid at 1.667, 1.667, and here is the red centroid at 2.2, 2.2. And now we go through all points, and we're going to ask which centroid is closer. Okay, so this first point, so now none of them are assigned. There is a line going from this first point to this centroid, and a line going from this point to the red centroid, and we can say, okay, the black centroid is closer. It's difficult to see here. Okay, here we take a look at this point, and we say which centroid is closer. And we say, okay, the black centroid is closer. What about this point? Which centroid is closer? The black centroid is closer. Which point is which centroid is closer? The black centroid is closer. Okay, what about these ones? Okay, these ones, the red centroid is closer, red centroid is closer, red centroid is closer, red centroid is closer. All right, and so this is what we get after reassignment. We say, all right, assign every point to the centroid that is closer. So these 4 points get assigned to the black centroid. These 4 points get assigned to the red centroid. Once we do that, we recalculate the centroids. We say, okay, what is the mean of the points assigned to the black centroid? Okay, what's the mean of these points? It's going to be right here. What's the mean of the points assigned to the red centroid? It's going to be right here. So if we do that, we get 0.5, 0.5, 3.5, 3.5, and this is what we get, all right? And then technically we would go through one more iteration. We'd say which centroid is closer, and we would go through, and all 4 of these points, this centroid is closer. All 4 of these points, the red centroid is closer. So no points get reassigned, right? So none of them is going to flip assignment, and so at that point we have converged. And so for this very simple toy data set, the K-means clustering algorithm has worked in terms of finding 2 clusters that make sense to us. Okay, and that's that. That's the K-means clustering algorithm right there. Let's try this out with a slightly bigger example. Okay. All right. So here, I generated 3 clusters of points using random multivariate normal. Okay. And I generated some points over here, some points over here, and some points over here. Okay. Again, the idea is when you're presented the data, none of it's labeled. Okay. So here we see red, black, and green, but in reality, it's just going to all come in completely unlabeled. We have no idea if any of these points even belong to different clusters. And we're going to just say, hey, can we identify some structure in here? Can we group some points together? Okay. All right. And so what we're going to do is we're going to just say, hey, let's see if we can identify 3 clusters in the data. All right. Now that's an arbitrary choice. When the data comes in, you don't know how many clusters you should be looking for. Right? So you can say, well, should I look for 2 clusters, 3 clusters, 4 clusters, 5 clusters? You don't really know, okay? We're going to start off kind of cheating, and we're going to just say, let's look for 3 clusters, and let's hope we're right, okay? So the data come in completely unlabeled. We're going to say, let's look for 3 clusters, and the first thing is we're going to just randomly assign all of our points to one of the 3 clusters. Okay, so some points we randomly assign to red, some points we randomly assign to green, some points we randomly assign to black. Right. Is that okay? So that's what we have here. We've got red, green, we've got black. And we say, all right, now that we've randomly assigned some points to red, some to black, and some to green, let's calculate the mean of each of these centroids. Okay, or let's calculate the mean of these points, the centroids of each of these things. So if I go through and I say, all right, calculate the mean of all the red points, calculate the mean of all the black points, calculate the mean of all the green points, this is what I get, okay? And because of random assignment, they're similar but not exactly the same, right? And that's all we need, okay? So here I get, these are the centroids. And you know, as we would expect, they're all kind of like the centroids all in the middle, but they're not exactly the same. So I got the red centroid, the black centroid, and the green centroid. And the red and the black centroid are like really, really, really close to each other. But they're not exactly the same. And that's going to be enough to differentiate. Okay. And so the next step we're going to do is we're going to reassign every point to the closest centroid. So we just say, hey, what is the closest centroid? So if I start off with this point over here, the closest centroid, just by a little bit, is the green one. Okay? And pretty much all of the points over here, the closest centroid is going to be green. Okay? If I go over here, what's the closest centroid? It's just by a little bit, it's the red one. Okay? And so pretty much all of the points over here, the closest centroid is going to be red. Okay? Which points have black as the closest centroid? It's just like a tiny, tiny little sliver of points. Like maybe this point right here, these points, black is closer than green or red, and maybe just like this, like even maybe this point right here, right? So if you look at like, I don't know, it's really hard to judge, right? But there's just kind of like a small sliver of points that are going to be closest to black. But pretty much everything over here is going to be closest to green, and then everything over here is going to be closest to red. Let's see. This one, I don't know. Okay. Well, we have the computer to help us calculate these distances, and we can say, hey, which ones are closest? And so, anyway, at the next iteration, we're going to just color in all of the points that get are closest to green, closest to red, and closest to black. Okay. And so, after we reassign points, all of these get assigned to green, all of these get assigned to red, and I guess just these points right here get assigned to black, okay? And again, it is possible that by random chance, one of your centroids or clusters kind of zeroes out and that none of the points end up getting a centroid closest to it, or just one point or something. And that just might mean you have to restart. But usually it won't zero. You might get something like this, but it won't zero out, okay? Okay, so what's the next thing that we do? We say, okay, well, all of these points are now green. What is the centroid of all of the green points? It'll be probably something around here. We say, hey, what's the centroid of all of the red points? Probably something around here, okay? And then we say, what is the centroid of all of the black points? And then probably like right here? I don't know, okay? So we're gonna reassign, we're gonna recalculate the centroids, all right? And this is where we end up, okay? So the centroid of the green points, all of the points assigned to green here, centroid of all of the points assigned to red, centroid of all of the points assigned to black, okay? And now we do a reassigning of points, okay? So we say, all right, which points are closest to green? Okay, so everything over here is still closest to green. Everything over here is still closest to red. But now there's a bunch of points kind of in the middle that are closest to the black centroid. And so we're going to kind of basically, we say, okay, well, what's halfway between red and black? And maybe around this point. And then you can kind of form like you're going to get like so you have this, and then you want something kind of perpendicular to that. And so basically, this is going to divide what's closest to red and black here, okay? And so basically, these things will become assigned to black. These ones will stay assigned to red. And then similarly, we look at a line that kind of connects black and green, and then we say halfway through, something like that. I don't know, okay? And so probably these ones down here will get assigned to black, and these ones over here will stay assigned to green. Okay, and then so there you go, okay? I think, is that, that's the line right there. I hope these colors are okay. Can you guys see? All right, and so, so again, we reassign the points to the closest centroid. And then now that we've reassigned the points, we're going to recalculate the centroid. So we say, okay, for all of the points assigned to red, where is the centroid for red? And so red is going to probably shift over there. The centroid is going to shift over there. For the green ones, it's probably going to shift a little bit that way. And for black, it's probably going to shift a little bit higher. Okay, so they shift, and then we go through and we reassign points. And we get that. And then we go through, and we recalculate the centroid, reassign points. And then I think this is where it has converged. We can kind of go through. Oh, there was a change. So anyway, this is the final assignments here. Okay. Now, again, we had cheated, and so when we created our data, we knew that there were 3 clusters, and we can kind of compare the 3 original classes to our final clusterings, and like, did our clustering algorithm recover it? And I think there's really just one, maybe 2 points that got switched. Okay, so in the original data, this was a little bit of an outlier for the red, and this was a little bit of an outlier for black. And when we did our clustering, it came back and it said, you know what, I think this one should belong with red, and I think that one should belong with black. Okay, and that's just the clustering algorithm has no idea. It just says, hey, these points are closer over here, and therefore it goes over there. Okay. Coincidentally, when we did this, red ended up over here, black ended up over here, and green ended up over here when we kind of colored them in. Okay. When you run a clustering algorithm, the labels are completely arbitrary. Okay. It's very well possible that this ended up being the red cluster, this ended up being the green cluster, and this ended up being the black cluster, right? Because all it's saying is just these points go together in this group, these points go together in this group, and these points go together in this group. And what color you decided to like group the points together in is completely arbitrary, right? If I just gave you some things and I said make groups, maybe you would come to the same groups, but then which group you called group 1 and which one you called group 2 and which one you called group 3 is completely arbitrary. And so when you do clustering, you often run into this thing called the label switching issue, right? And so when you rerun the cluster, if you started off with another random seed and you ran K-means clustering, okay, you might actually end up with the same cluster assignments, except if you just run a pure, did cluster, this point ended up in cluster 1 last time, did it end up in cluster 1 this time? That's probably not going to happen, okay? Because you might get all of these points end up in the same cluster, but the first time you run it, this might get labeled the red cluster, and then the second time you run it, it might get labeled the black cluster, okay? And it's not that anything went wrong or anything even changed. It's just because of the random initial assignments, the label of the cluster has changed. Okay. For your homework, you're going to be writing up a little bit of an algorithm to perform K-means cluster. Okay. Now, the truth is, there's already a K-means clustering function in R, okay? And in reality, if you ever had to do K-means clustering, you'd probably just use R as K-means function. It's pretty good. But I think there's merit in writing your own little function and getting it working and going through the process of thinking about the algorithm and putting it into code, right? Okay. So here, when I ran K-means clustering in R, this one ended up green, this one ended up black, and this one ended up red, okay? And I think the assignments are actually exactly the same. So if you look at which points got assigned to this cluster over here, I think it's exactly the same as over here. So you look at these points, like these two got assigned to this cluster, and same thing over here. And you look at the boundary between this cluster and this cluster, and it's right along this kind of line here. And indeed, it's the same clustering. So same results, just again different labels. Okay. So and the algorithm is very simple. You just provide it the matrix of data, right? And here our data is 2-dimensional, but it could be higher dimensional, no problem. And then you say how many clusters are we looking for? We say we're looking for 3 clusters. Okay. And then the results, the cluster assignments come back in $ cluster. So if you store the results, I can just plot the data, color them using results $ cluster, and this is what we get. Okay. And so here we can see the assignments, and I think when I generated the data, the first 100 were part of cluster 1, the next 100 were part of cluster 2, and the last 100 were part of cluster 3. And so we could say we indeed this pretty much classified everything correctly. There were a couple outliers where the we had kind of two points that got kind of swapped or switched. Okay, and so this is the clustering vector. The results here. There is a measure called the within cluster sum of squares. And the idea here is after running the clustering, the distance, if you look at the sum of squares, as in like if this is the centroid and you ask what's the distance to each centroid, it's going to be smaller than if you just had one centroid for all the data, which might be somewhere around here. And you say, what is the sum of squared distances from that one? So the total sum of squared is just what would the distances be to just one centroid for all the data versus what is the distances for to the centroids for each of the different clusters. It's kind of like the in ANOVA, you have you guys took 101B, right? So in ANOVA you have the between sum of squares and within sum of squares, or total sum of squares and between sum of squares, right? And so if you have 3, it's just, for ANOVA it's 1-dimensional, but you have the sum of squares to the means of each group compared to the total sum of squares, which is basically your variance multiplied by n minus 1. So you have the total sum of squares, and then the between sum of squares, and that ends up being kind of your, that factors into your R squared value, right? So this is kind of like an R squared value for how much your between sum of squares accounts for the total sum of squares. So we get that. Let me give you did I give you your second view quiz? Not yet. Okay, second view quiz answer is B. B as in bear, B. Okay. Let me show you what would happen if I just change the number of clusters that I'm looking for. So here I say, let's look for 2 clusters. Okay. If I look for 2 clusters, it just splits it basically in half. It says these ones go to the black cluster, these ones go to the red cluster. Okay, that's looking for 2 clusters. Okay. If I look for 4 clusters, we end up we get this. Okay, so it finds a green cluster, a black cluster, a blue cluster, and a red cluster. So that's with k equal to 4, and that's with one random starting seed. If I did k equals 4 again, just change the starting seed, I end up getting a different cluster assignment. Okay, and again, so these assignments are stable in that if I calculate the mean of the red cluster, I calculate the mean of the green cluster, calculate the centroid or mean of the blue cluster and the black cluster, all of these points are closest to the blue cluster. Nothing will get reassigned. If I look at the red or the green cluster, then find the centroid there, all of these points would get assigned to the green centroid, and nothing will get reassigned. So these assignments are stable, and these assignments are also stable, but they're different. Okay, maybe these ones, did these points end up in the same? No, not quite, because this one ended up in the other group as well. Okay, so with k equal to 4, we end up getting different results. Okay, and that would be a sign to you that maybe this is not the universal number of clusters. Okay, but how many clusters, again, how many clusters is such an impossible question to answer, okay? It really is. So it's as impossible as how many, so if you think about like the census form, okay? And there's a spot where you put in race or ethnicity, okay? How many races or ethnicities should be on that form? And the answer is, I don't know, right? It's very, very, very difficult to say how many like groups exist that are more similar to each other than different from each other, right? And, you know, so like you could have, so depending on different contexts and things, okay, you could have, you could say there's white versus non-white or person of color, right? You can have white, black or African American or of African descent, and other races or ethnicities, and you know, you can have put in Asians as a group. That could further be divided into, you know, East Asian, South Asian, Southeast Asian. You know, for East Asians, that could be further divided into Chinese, Japanese, Korean. And, you know, if you look at Chinese, that could even be further divided into, you know, different racial groups within, you know, the Chinese population. And so how many clusters should we find or look for? It's very, very challenging, okay? And then surely, you know, how many races or ethnicities, that's also politically fraught and challenging. But just even in some innocent context of just, here we've got points here, all right? It's not exactly known, okay? And so there's a few kind of tools we can use to help try to figure out how many clusters we should look for, but again, it's quite difficult, right? So here, with k equal to 4, one thing we can look at is we could look at the within sum of squares and between sum of squares value. Here we got 87.8. Over here we got 88.0, okay? And if you look at these numbers, it's some of the clusters end up with smaller, right? So this one ends up with 78 and 79, and that's probably the blue and the green over here. And over here, we end up with, you know, one cluster ends up 59 and the others end up in the 100-somethings. Okay, so the 59 cluster is probably the smallest one right here. it's hard. So one thing I did was I just ran kind of this double for loop where I did 20 different runs of the same k-means. So I started off with k equal to 1, and I'm going to look for up to k equal to 10. And I did 20 runs with k equal to 1. Okay, that's kind of silly because I'm going to get the identical results every single time. Okay, but I also did 20 runs of k equal to 2. I did 20 runs of k equal to 3. I did 20 runs of k equal to 4. Probably k equal to 2 and k equal to 3 probably will result in almost the same results every single time. With k equal to 4, we can just see, at least with 2 runs, we got different results, okay? And if I did 20 different runs, how different would my results be, okay? So I kept track of all of these things, and I'm gonna just keep track of the total within sum of squares, which is basically 1 minus the between, right? So total minus between will give us the within, the total within sum of squares. Okay, so these are the results. So we can see for k equal to 1, all 20 results ended up with exactly the same, which is exactly what we would expect. With k equal to 2, at least these first few looks like they're all exactly the same. And then looking at the tail end, with k equal to 9, we can see we get some variation. 307, 262, 282, 278. With k equal to 10, we get some variation as well. 258, 230, 244, 263, and so on and so forth, okay? And so sometimes, even though with k equal to 10, so in general, as you increase your k, your within sum of squares is going to decrease. Just kind of like increasing more variables, your r squared value keeps going up. So we can see there's some variation. And so here's a little bit of a box plot, okay? So here there's no variation, okay? And there's just a tiny bit of variation over here. And the question is, you know, at what point does the kind of increase in sum of squares not benefit, okay? And so we see a huge drop from 1 to 2 as expected, but even big drop from going from 2 to 3 sum of squares, or three clusters, but then going from 3 to 4, 4 to 5, 5 to 6, your amount of how much your within sum of squares decreases only changes by a little bit, okay? And so that's again, how many clusters should you look for? It's quite difficult. If you're able to accommodate many clusters, then great. If you're in a situation where you're just looking for broad general categories, you can kind of say, well, let's only just pick a couple of clusters. And then again, you want to be sensitive to the idea that if we were to rerun the clustering algorithm, you might end up getting different results each time, okay? You might, especially, you know, with something like k equal to 4, k equal to 5, you might get different results every time you run it. And so a lot of these things require multiple runs, and kind of maybe you say, well, the majority of these runs end up forming these clusters, and therefore we think these should be the clusters that we form. But it's kind of a loose, it's not an exact science here, okay? It's there's definitely room for interpretation, and exactly how many clusters to look for, again, is oftentimes a very difficult or impossible question to answer. Okay, that's it for today's lecture. Let me give you your last view quiz answer, which is the letter A. A as in apple. A as in apple. That is your last view quiz answer. Okay, we'll end there. We'll see you on Wednesday.